What if I told you that the very fabric of reality, the universe we see, the stars we gaze at, even the ground beneath our feet might have begun as nothing more than a cosmic coin toss? A flickering, uncertain state where everything and nothing existed all at once. This isn't science fiction, it's the mind-bending heart of quantum mechanics, a realm where particles defy logic, existing in multiple places, multiple states until the moment we look. And here's the wildest part: this strange phenomenon called quantum superposition might hold the key to understanding how our universe was born. Think about that for a second. Before there were galaxies, before there was light, even before time itself had a clear direction, the universe could have been a swirling sea of possibilities, a quantum haze where every potential outcome played out simultaneously. It's as if the cosmos began with a question rather than an answer, and today, scientists are piecing together theories about how that primordial quantum fog collapsed into the reality we know. Some say it was the first act of observation, a cosmic measurement that snapped everything into place. Others believe it was a cascade of quantum events, like dominoes falling across the fabric of space-time. That's where this journey begins. Over the next 30 theories, we'll explore the most daring, provocative ideas about how quantum superposition shaped the universe from its very first moments. From parallel realities branching off like threads in a tapestry, to hidden dimensions folded into the fabric of space, these aren't just thought experiments, they're windows into the deepest mysteries of existence. So buckle up, because we're about to dive into the quantum unknown, where the rules of common sense don't apply, and where the universe's greatest secrets might just be waiting to surprise us. To grasp just how bizarre the birth of the universe might have been, picture an endless, silent void, not empty, but crackling with invisible energy. This is the quantum vacuum, a seething ocean of potential where particles flicker in and out of existence like sparks in the dark. According to the Quantum Fluctuation Hypothesis, our entire cosmos could owe its existence to a single, unimaginably rare ripple in this void. One moment there's nothing but probability, the next, a quantum blip tips the scales and reality crystallizes around it. It's like shaking a soda bottle. Tiny bubbles form randomly, but under just the right conditions, one triggers a chain reaction. In the quantum world, these spontaneous fluctuations aren't just noise, they're the universe's raw ingredients. Modern quantum field theory suggests that even in total emptiness, fields permeate everything, vibrating with untapped energy. Occasionally, these vibrations sync up, amplifying into something tangible. And if the math holds, one such event could have stretched from a microscopic quirk into the Big Bang itself. What's even wilder, this might explain why spacetime exists at all. Before stars, before atoms, before dimensions as we know them, the first quantum blip could have stretched and warped the fabric of reality like a drop of ink in water. Some physicists argue that time itself emerged from this instability, an arrow born from chaos. So when we look at the night sky, we might be seeing the echo of that original fluctuation, frozen in the cosmic background radiation like a fingerprint. Critics push back, of course. If quantum jitters spawn universes constantly, why don't we see others? Supporters counter that new universes might bubble away in dimensions we can't perceive, each with its own rules. It's a humbling thought. Our majestic cosmos, with its swirling galaxies and symphonies of physics, might just be one accidental masterpiece in an infinite gallery of possibilities. Now imagine reality not as a solid, three-dimensional stage, but as a shimmering projection, a cosmic illusion painted onto the surface of something far stranger. This is the holographic principle, a theory so radical it suggests our universe's first quantum superposition wasn't just a state of matter, but a shadow cast by information written on the fabric of spacetime itself. Picture a black hole. According to groundbreaking work by physicists like Leonard Susskind, all the information about what falls into a black hole isn't lost, it's smeared across its event horizon like ink on a balloon. Stretching this idea to the cosmos, the holographic principle proposes that our entire universe might work the same way. What we perceive as three-dimensional reality, galaxies, planets, even our own thoughts, could be a hologram generated by quantum bits dancing on a distant, two-dimensional surface. Here's where it gets wild. If true, the universe's earliest moments weren't just a quantum soup, they were a cosmic data transfer. The Big Bang might have been the moment this lower dimensional code, rendered into the reality we know, like a projector flickering to life. String theorists take it further, suggesting the holographic boundary could be where entangled quantum particles, those spooky twins that mirror each other across space, first synchronized, weaving the fabric of spacetime itself. Critics ask, how could flat information create depth? Think of a security hologram on a credit card. Tilt it, and a 3D image emerges from flat stripes. The holographic principle argues reality does something similar, with quantum entanglement acting as the hidden threads stitching the illusion together. So next time you gaze at the stars, consider this. Their light might not just travel through space, it could be pixels in the ultimate cosmic display, echoing from a screen we'll never see. What if our universe wasn't the first or the last to emerge from the quantum haze? Imagine a vast cosmic tree, its branches endlessly splitting, each one a new reality sprouting from the decay of another. This is the multiverse bootstrap theory, a mind-bending idea suggesting our universe didn't arise from nothing but was instead kick-started by the quantum collapse of a parent universe. It's like a cosmic game of dominoes, where one universe's demise becomes the spark for another's birth. At the heart of this theory lies quantum tunneling, a phenomenon where particles cheat the rules of classical physics, slipping through energy barriers they shouldn't be able to cross. Picture a ball rolling up a hill on its own, impossible in our everyday experience, but routine in the quantum realm, now scale that up to universe-sized proportions. In the eternal inflation model, pockets of spacetime constantly bubble up and decay within an endlessly expanding multiverse. Occasionally, a quantum fluctuation inside one of these bubbles tunnels through the energy barrier, creating a new, stable universe with its own laws of physics. Ours could be just one such lucky outlier. The implications are staggering. If true, our Big Bang might have been less of a singular explosion and more like a cosmic relay race, with the baton passed from a dying universe to a newborn one through quantum decay. Some versions of this theory even suggest that the parent universe's quantum superposition, its unresolved state of infinite possibilities, literally bled into ours, imprinting its quantum weirdness into the fabric of our reality. That could explain why entanglement and superposition feel so fundamental to our universe's workings, their inherited traits. Critics argue this pushes the boundaries of testability, but proponents point to subtle fingerprints. If our universe was born from tunneling, its initial energy state would carry a specific signature like a birthmark in the cosmic microwave background. Others speculate that quantum entanglement between universes might leave faint traces, like shadows in the math of particle physics. Here's the poetic twist: if every universe seeds others through quantum decay, then existence becomes an unbroken chain stretching infinitely backward and forward. We're not just stardust, we're the reverberation of a quantum tremor that began who knows how many universes ago, and somewhere out there, another reality might be forming right now from the remnants of our own. But what if time isn't a one-way street? What if the universe doesn't just begin and end, but cycles endlessly, with each iteration carrying quantum echoes of the past? This is the spine-tingling premise of Roger Penrose's Cyclic cosmology, a theory where the Big Bang wasn't the absolute beginning, but a cosmic reboot. In Penrose's vision, our universe's first quantum superposition might not have been a random fluctuation, it could have been a relic, a whisper of quantum states left behind by a previous eon, a universe that existed before ours. At the heart of this idea lies conformal cyclic cosmology, a framework where the infinite expansion of one universe seamlessly morphs into the high-energy singularity of the next. Imagine the universe stretching so thin over eons that all matter evaporates, all particles decay, and even black holes dissolve into radiation. At this point, space becomes eerily smooth, no stars, no atoms, just pure, featureless energy. And here's the twist: this state mathematically looks identical to the ultra-dense singularity of the Big Bang. Time loses all meaning, the end becomes the beginning. Penrose argues that quantum information, particularly the spin states of particles, could somehow survive this transition, imprinting the new universe with remnants of the old. It's as if the quantum superposition we observe today, those particles existing in multiple states at once, are cosmic heirlooms, handed down through cycles of creation and destruction. This could explain why quantum mechanics feels so fundamental. It's not just the language of our universe, it's the echo of countless universes before it. The implications for time's arrow are staggering. Normally, we think of time as flowing from order to chaos, from the Big Bang's pristine uniformity to the scattered randomness of entropy. But in Penrose's model, entropy resets with each new eon, while quantum information subtly lingers. Some physicists speculate that this could create a hidden thread of causality linking universes, like a cosmic game of telephone, where each cycle tweaks the rules slightly. Critics question how quantum states could survive the total dissolution of spacetime. Penrose's answer: gravitational waves. He and collaborators have searched for faint, circular patterns in the cosmic microwave background, potential fingerprints of black hole collisions from a prior eon. These Hawking points could be smoking gun evidence of cyclic time. So if Penrose is right, the quantum weirdness we grapple with today, the superposition, the entanglement, might not be quirks of our universe. They could be messages from a forgotten past, written in the fabric of reality itself, and someday when our universe fades to nothing, its quantum whispers might birth another cosmos, carrying fragments of our story into the next cycle of eternity. Ever wonder what it would mean for time itself to be an illusion, a cosmic sleight of hand emerging from something deeper? That's the radical proposition at the heart of the Wheeler-DeWitt equation, a mathematical framework so profound it dissolves time entirely from the universe's fundamental description. Picture this: before clocks ticked, before stars aged, even before the Big Bang's fiery dawn, reality might have existed in a frozen, timeless quantum state, a single, eternal wave function holding every possible configuration of the cosmos at once. The equation, crafted by physicists John Wheeler and Bryce DeWitt in the 1960s, was an attempt to merge quantum mechanics with general relativity. But it did something unexpected. When they plugged in the numbers, time vanished from the math entirely, not slowed down, not hidden, gone. It's as if the universe's deepest blueprint was a snapshot, not a movie. In this view, the first quantum superposition wasn't just a momentary flicker, it was the universe's entire existence, suspended in an unchanging quantum haze until something, somehow, collapsed it into the flowing, time-bound reality we know. How does this solve the problem of time? Quantum gravity theorists argue that time might be an emergent property, like temperature arising from the random motion of atoms. At the most fundamental level, there's no before or after, just a vast interlocking web of quantum possibilities. The ticking of clocks, the expansion of galaxies, even our own experience of cause and effect could be side effects of this timeless quantum soup organizing itself. Here's where it gets even stranger. Some interpretations suggest that the act of observation, conscious or otherwise, might have played a role in unfreezing the wave function. Imagine the universe as a dormant computer, its screen dark until someone presses the power button. In this analogy, the Wheeler-DeWitt equation describes the sleeping machine, and our measurements could be the keystrokes that wake it up, rendering time and change as features of the display rather than the hardware. But if time isn't fundamental, why does it feel so real? Proponents point to quantum decoherence, the process by which superposition states pick a concrete outcome through interaction with their environment. Applied cosmically, the universe's own quantum jitters might have triggered its decoherence, breaking the timeless symmetry and spawning the arrow of time we experience. Critics counter that a timeless universe struggles to explain causality. How can one event lead to another if there's no next in the fundamental math? Supporters reply that causality itself might be emergent, a higher-level pattern woven from timeless quantum threads. The most haunting implication, if the Wheeler-DeWitt equation is correct, then deep down beneath the whirl of galaxies and the pulse of particles, the universe might still be timeless. Our perception of time, of beginnings and endings, could be a shimmering mirage on the surface of something far more alien, an eternal, unchanging quantum sea. And that means the universe's first superposition wasn't an event in time at all, it was time's birth cry, echoing from a void where, when had no meaning. Imagine a cosmic courtroom where reality itself is on trial, not by a judge, but by the relentless jury of the environment. This is the essence of quantum Darwinism, a theory proposing that the universe's first quantum superposition didn't just collapse randomly, but was sculpted by a process akin to natural selection. The idea flips the script on how we think about reality's origins. Instead of observers creating the classical world by looking, the environment chooses which quantum states survive by interacting with them over and over, until only the most robust remain. It's survival of the fittest, but for facts. At its core, quantum Darwinism hinges on decoherence, the phenomenon where quantum systems lose their fuzzy, multiple-state existence by bumping into their surroundings. Picture a drop of dye in water. At first it's concentrated, coherent, but as molecules collide with it, the dye spreads, blending irreversibly into the liquid. Quantum states work similarly. In the early universe, every particle, every field was entangled in a vast superposition, but as they interacted with each other, exchanging photons, gravitons, or other quantum handshakes, their delicate quantumness leaked into the environment, leaving behind only the states resilient enough to leave consistent imprints. These imprints became our classical reality. Here's the twist: this process might explain why spacetime even exists. Think of space as a network of relationships between objects. In a pure quantum haze, distances and directions are fluid. An electron could be both here and a light year away, but through countless environmental interactions, certain spatial configurations win out, becoming stable enough to frame the universe we recognize. Time, too, could emerge from this Darwinian fray. If quantum states constantly compete to leave environmental records, their succession might create the illusion of a flowing timeline, like frames in a movie appearing continuous only because they flip fast enough. The implications for observers are profound. Traditional quantum theory says measurement collapses the wave function, but quantum Darwinism suggests observers, whether humans, particles, or black holes, don't create reality. They just stumble upon the version of it the environment has already voted into existence. Your brain doesn't make the moon real by looking at it. It simply latches onto the moon's quantum signature, which has been broadcast into the cosmic background by eons of photon collisions. Critics ask, why do we all see the same moon then? Supporters argue that the environment acts as a universal ledger, amplifying certain quantum states until they're impossible to ignore. It's like a viral tweet reposted enough times, it becomes consensus reality. This could also solve the mystery of why quantum effects fade at large scales. A single electron can be in two places at once, but a baseball can't, because its trillions of particles constantly vote on their collective state through environmental chatter. The most tantalizing possibility, if quantum Darwinism is true, the early universe's superposition didn't vanish, it fossilized. The cosmic microwave background, the distribution of galaxies, even the constants of physics might be relics of that primordial selection process. We're not just living in a universe, we're living in the version of it that outcompeted countless alternatives, etched into existence by the silent, ceaseless jury of quantum noise. Now consider a universe where the deepest truths aren't hidden in the stars or the atoms, but written on the edges of reality itself, like a message scrawled on the inside of a cosmic sphere. This is the bizarre promise of the ADS/CFT correspondence, a revolutionary idea in theoretical physics that suggests our three-dimensional universe, with all its quantum complexity, might be nothing more than a holographic projection from a lower dimensional boundary. Think of it like watching a movie on a flat screen. Every explosion, every tearful goodbye, every galaxy spinning in the background is just light dancing on a two-dimensional surface. The ADS/CFT duality proposes something similar for reality, that the universe's first quantum superposition wasn't confined to the space we see, but was instead a shimmering pattern of information painted onto a distant, invisible canvas. At the heart of this idea lies a mathematical bridge between two seemingly unrelated theories, a type of spacetime called anti-de Sitter space, a negatively curved universe that bends inward like a saddle, and conformal field theories, which describe quantum particles living on that universe's boundary. What's staggering is that these two frameworks, one describing gravity in bulk space and the other describing quantum fields on its edge, turn out to be mathematically equivalent. It's as if the universe's entire instruction manual was rewritten in a language where depth is an illusion, and every particle collision, every black hole's birth is just a shadow play performed by quantum data on a distant wall. This gets even wilder when we connect it to black holes. Remember the holographic principle? ADS/CFT takes it further, suggesting that a black hole's interior, including the infamous singularity, might be entirely encoded on its event horizon. That means the terrifying firewall paradox, where quantum theory predicts a wall of searing energy at the horizon, could be resolved by realizing the firewall isn't inside the black hole at all. It's part of the hologram, a glitch in the cosmic projection. Here's why this matters for the universe's first moments. If the ADS/CFT duality holds, the Big Bang might not have been a fiery explosion in space. It could have been the moment a lower dimensional quantum code rendered into the three-dimensional reality we perceive. Imagine a quantum computer booting up a simulation, except the simulation is us. The early universe's superposition wouldn't have been a chaotic soup of particles, it would have been a meticulously arranged quantum algorithm on a boundary we can't see, humming with potential until it crystallized into spacetime. Critics argue that our universe isn't anti-de Sitter space, it's expanding, not curved inward, but supporters counter that the math might still hold clues, like a rough draft of a deeper truth. Some even speculate that quantum entanglement, the spooky link between particles, is the glue binding the hologram together. Entangled particles could be threads stitching the projection together, their connections mirroring the way pixels cooperate to form an image. So if the ADS/CFT correspondence is right, the universe's first quantum state wasn't just a flicker of possibility, it was the first line of code in a cosmic program, running on hardware we'll never touch. And every law of physics, every star in the sky, might just be the output of a calculation happening on the edge of everything. Let's shatter everything you think you know about space and time. What if the universe wasn't born in a fiery explosion, but in a cosmic bounce, a rebound from a previous collapse so violent that it shattered spacetime itself into tiny, vibrating loops? That's the jaw-dropping premise of loop quantum gravity, a theory where reality isn't smooth and continuous, but woven from microscopic threads of quantized space. Imagine the fabric of the cosmos as a tapestry made of spinning threads, each one a fundamental grain of spacetime, intersecting and braiding to form the world we see. And here's the kicker, These threads, called spin networks, might hold the secret to the universe's first quantum superposition. In this radical framework, the Big Bang wasn't a singular beginning, it was a big bounce. Picture a universe collapsing under its own gravity, squeezed into a space smaller than an atom. Normally, you'd expect it to vanish into a singularity, a point of infinite density. But loop quantum gravity says no. When spacetime gets compressed beyond a certain scale, it doesn't collapse, it rebounds like a spring hitting its limit. The violent energy of that rebound, that's our Big Bang, but here's where quantum superposition enters the picture. Before the bounce, the spin networks describing spacetime would have been in a chaotic, fluctuating state, a quantum foam where every possible configuration of loops existed simultaneously. The bounce itself could have been the moment these superpositions collapsed, crystallizing into the stable spacetime we recognize today. Why is this revolutionary? Because it solves two cosmic mysteries at once. First, it banishes the singularity, no more infinities breaking physics. Second, it explains why quantum weirdness feels baked into reality. If the universe emerged from a quantum haze of spinning loops, then entanglement and superposition aren't quirks, they're leftovers from that primordial quantum storm. Even now, hidden beneath the apparent smoothness of space, these spin networks might still be humming, vibrating at the smallest scales like the strings of a cosmic guitar. Critics argue loop quantum gravity is hard to test. How do you measure spacetime grains trillions of times smaller than an atom? But supporters point to subtle clues. If spacetime is granular, high-energy cosmic rays should stumble on those tiny bumps, leaving faint fingerprints in their spectra. Others speculate that gravitational waves from the Big Bounce might still echo in the cosmic background, waiting to be heard. The most poetic idea: if the universe cycles through bounces, then every collapse plants the seeds for a new superposition, a fresh quantum genesis. Our reality might just be one link in an endless chain, each iteration inheriting a whisper of the last. And somewhere out there, another universe's loops could be winding tight, ready to bounce into being when ours fades to black. Picture this: you wake up, not in your bed, not in any recognizable place, but floating in an endless void. Your memories feel real: the taste of coffee, the warmth of sunlight, but here's the terrifying twist: you might not exist at all. You could be nothing more than a random quantum hiccup, a fleeting thought generated by the cold, chaotic dance of particles in an otherwise lifeless universe. This isn't the plot of a sci-fi nightmare. It's the Boltzmann brain paradox, one of the most unsettling ideas in physics, and it forces us to confront a spine-chilling possibility that the universe's first quantum superposition didn't birth galaxies or stars, but isolated, self-aware illusions. The paradox takes its name from Ludwig Boltzmann, the 19th century physicist who realized that in an infinite universe, even the most improbable events must happen eventually. Fast forward to quantum mechanics, and the idea mutates into something even stranger. In a vast thermal void, a cosmos that's mostly empty, cooling toward maximum entropy, random fluctuations could, by sheer chance, assemble atoms into a functioning brain. Not attached to a body, not rooted in any reality, just a lone consciousness flickering into existence, complete with false memories of a universe that never was. Why does this matter for quantum superposition? Because if the universe began as a quantum haze of possibilities, the Boltzmann scenario suggests that the most likely outcome wasn't a grand, structured cosmos, but a sea of disconnected observers. Think of it like shaking a box of puzzle pieces. The odds of them randomly forming a complete picture are astronomically low, but the chance of a few pieces accidentally lining up. That happens all the time. In quantum terms, a fully coherent universe might be the puzzle. A Boltzmann brain is just two pieces sticking together momentarily. The implications rip through science and philosophy alike. If consciousness can emerge from quantum noise, how do we know we're not Boltzmann brains right now? Supporters of the multiverse theory argue that in an infinite landscape of realities, some must be populated by these phantom minds. Critics fire back, if we're just fluctuations, why does reality feel so consistent? Why do the laws of physics hold firm, and why do our memories align with external evidence? Here's where it gets even weirder. Some physicists propose that the universe's quantum decoherence, the process that collapses superposition into concrete reality, might actively suppress Boltzmann brains. Like a cosmic immune system, the laws of physics could favor stable, structured worlds over chaotic, self-deceiving ones. Others suggest that the very act of observation anchors reality, making shared experiences more real than solitary hallucinations. But the paradox lingers, a ghost in the machinery of cosmology. It forces us to ask, is the universe we see the most probable outcome of quantum beginnings, or are we just lucky or unlucky enough to be the ones asking the question? And if our existence is a statistical fluke, what does that say about the nature of reality itself? Maybe the answer isn't in the stars, but in the silence between them, where quantum possibilities still whisper, waiting to be born or to dissolve into nothingness, like a thought forgotten in the dark. What if the universe needed a witness to spring into being, not a god, not a cosmic accident, but a conscious mind to force reality into focus? This is the provocative heart of the von Neumann-Wigner interpretation, a quantum theory so audacious it puts consciousness itself at the center of creation. Picture the early universe as a swirling quantum fog, every possible version of existence overlapping in a dizzying haze. According to this idea, that fog didn't lift because of random chance or environmental noise. It snapped into clarity the moment it was observed. Not by a machine, not by a particle collision, but by something aware enough to say, "This is real." The roots of this theory stretch back to the dawn of quantum mechanics. Physicists John von Neumann and Eugene Wigner wrestled with a perplexing question: why does measurement collapse a quantum superposition? The math said particles existed in multiple states until observed, but no one could explain what constituted an observer. Their radical answer, consciousness itself. They proposed that the universe's first quantum superposition persisted until a self-aware entity, perhaps an early form of life, or even a primordial cosmic mind interacted with it, freezing the quantum possibilities into a single, tangible reality. Here's where it gets metaphysical. If consciousness causes collapse, then the universe isn't just described by quantum mechanics, it's shaped by it, with sentient beings as co-creators. It's as if reality is a grand orchestra waiting for an audience to hear it before the music truly exists. Some modern supporters take this further, suggesting that life isn't an accident of physics but a necessary ingredient, weaving the fabric of existence through observation. In this view, the Big Bang wasn't complete until the first conscious observer blinked awake somewhere in the cosmos. Critics pounce on two glaring issues. First, testability. How do you design an experiment to prove consciousness collapses wave functions? Detectors and lab equipment are made of particles, why wouldn't they count as observers? Second, the specter of solipsism. If reality hinges on observation, does a tree falling in an empty forest make a sound? Or worse, are we alone in the universe, with everything else just a projection of our own awareness? Supporters counter with modified versions of the theory. Maybe consciousness doesn't cause collapse but participates in it, entangled with quantum systems through feedback loops. Others propose that even rudimentary forms of awareness, like the information processing in single-celled organisms, could nudge superpositions toward stability. There's also the eerie twist of retrocausality. If consciousness affects quantum states, could future observers be influencing the past, including the universe's birth? The irony is delicious. A theory born from cold, hard math ends up echoing ancient philosophical idealism, the idea that reality is fundamentally mental. But whether you see it as profound or pseudoscientific, the von Neumann-Wigner interpretation forces us to confront a haunting possibility that the universe's first quantum leap wasn't just a physical event, but a moment of recognition, a cosmic aha that whispered into the void, "Let there be something." And if that's true, then every time we look at the stars, we might not just be studying the universe, we might still be helping to build it. Now imagine the universe not as a smooth continuum, but as a vast, shifting web, a cosmic mesh where even space and time are stitched together from something deeper. This is the quantum gravity framework, a theory so radical it suggests our entire reality crystallized from a seething network of quantum connections, like ice forming on the surface of a stormy sea. At its core lies a mind-bending idea. What if spacetime itself was born from a primordial soup of abstract mathematical links, flickering in and out of existence until click, they suddenly locked into place, freezing the first quantum superposition into the geometry we call the universe. The name graphity is a play on words. Graph theory meets gravity. Picture the early cosmos not as a void, but as an infinite, boiling graph where every point is a node, and every link between them is a fluctuating quantum bond. In this frenzied state, distances and directions meant nothing. A node might be connected to a million others, or none at all. Time didn't flow, it hopped erratically between connections like a bee drunk on pollen. Then, as energy bled away, something extraordinary happened. The graph cooled and those chaotic links began to stabilize, organizing into a regular lattice, a cosmic grid where certain paths became privileged, defining the axes of space and time we know today. Here's where gravity enters the picture. In traditional physics, gravity is a fundamental force bending spacetime, but in the quantum gravity framework, gravity isn't fundamental at all, it's an illusion, a side effect of the graph structure. Think of it like traffic flow in a city. The shortest path between 2 points isn't a straight line, it's whatever route has the fewest stoplights. Similarly, what we perceive as gravity's pull could just be particles finding the most efficient path through the graph's tangled connections. This is emergent gravity, a phenomenon where the force we feel is really just geometry in disguise. What makes this theory electrifying is how it reimagines the first quantum superposition. Before crystallization, every possible configuration of the graph existed at once, a superposition of potential universes, each with its own set of physical laws. The moment the graph froze, one configuration, and with it our particular flavor of reality. Some versions of the theory even suggest that defects in the graph, places where the lattice didn't align perfectly, could explain dark energy or the universe's accelerating expansion, like cracks in a frozen lake pulling everything apart. Critics argue that quantum gravity struggles to explain why the graph crystallized the way it did, why 3 spatial dimensions, why the specific strengths of forces we observe. Supporters counter that the answer might lie in the math of phase transitions, the same physics that makes water turn to ice at 0 degrees, just as ice crystals form in hexagonal patterns because it's the most stable arrangement. Spacetime's 4-dimensional structure could be the graph's lowest energy state. The most startling implication: if spacetime is a crystal, it might have flaws, places where the lattice warps or breaks. These cosmic defects could be portals to pre-graph realities, or even windows into other dimensions. And somewhere out there, patches of the original quantum graph might still exist, bubbling with alternate physics, waiting to be discovered. So the next time you look up at the night sky, remember, you're not just gazing at stars, you're seeing the shadow play of a quantum network that chose, long ago, to snap into focus. And that choice might still be echoing through every atom in your body. What if the key to the universe's first quantum superposition wasn't hidden in particles or fields, but in the invisible thread stitching reality itself together? That's the electrifying promise of the ER equals EPR conjecture, a theory so daring it proposes that quantum entanglement, the spooky connection between particles across vast distances, is secretly the same thing as wormholes, the cosmic shortcuts through spacetime. Imagine the early universe not as a chaotic soup of matter, but as a vast, humming network of entangled particles, each connection forming a microscopic bridge through the fabric of reality. In this view, the first quantum superposition wasn't just a state of uncertainty, it was a labyrinth of quantum tunnels, weaving the cosmos into existence one entangled handshake at a time. The idea was born from two seemingly unrelated breakthroughs, EPR named after Einstein, Podolsky, and Rosen's famous 1935 paper, describes how entangled particles share a single quantum state, no matter how far apart they are. Change one and the other instantly responds, as if space between them doesn't exist. ER, on the other hand, refers to Einstein and Rosen's later work on wormholes, hypothetical tunnels connecting distant points in spacetime. For decades, these concepts lived in separate worlds. Then in 2013, physicists Juan Maldacena and Leonard Susskind dropped a bombshell. What if entanglement and wormholes are two sides of the same coin? Here's where it rewrites the universe's origin story. If entanglement creates microscopic wormholes, then the cosmos might have begun as a quantum web, with every particle linked to every other through a maze of spacetime threads. Superposition, the ability of quantum systems to exist in multiple states at once, wouldn't just be a quirk of particles, it'd be the gravitational echo of these hidden wormholes, flickering in and out of existence like cosmic switchboards. Picture a galactic internet, where information doesn't travel through space but tunnels beneath it, preserving quantum coherence across the entire universe. The implications for unifying quantum mechanics and gravity are staggering. Quantum theory thrives on unpredictability, while general relativity paints spacetime as smooth and deterministic. The ER equals EPR bridge suggests that spacetime itself emerges from quantum entanglement, that the geometry of the universe is literally woven by these threads. Black holes, the nemesis of this unification, might be the ultimate test case. When particles fall into a black hole, their information seems lost forever, violating quantum rules. But if entanglement creates wormholes, that information could be secretly threaded through spacetime, emerging elsewhere like a message slipped through a hidden pipe. Critics argue the conjecture is still more math than physics. How do you prove a wormhole is just entangled particles? Supporters point to the firewall paradox, a crisis in black hole physics where quantum theory predicts a wall of fire at the event horizon, while relativity says you'd notice nothing. ER equals EPR offers a way out. The wormhole links particles inside and outside the black hole, making the firewall vanish into the geometry of spacetime itself. The most poetic twist, if this conjecture holds, the universe's first quantum state wasn't a featureless void, it was a cosmic loom, spinning the fabric of reality from entangled threads. Every star, every planet, every atom in your body might still be connected by these invisible stitches, remnants of that primordial quantum weave, and somewhere in the depths of space, those threads might still be vibrating, humming the universe's oldest song, a melody of entanglement played on the strings of spacetime. What if time and space aren't smooth and flowing, but made of tiny, indivisible moments like frames in a cosmic film reel? That's the bold claim of causal set theory, a framework where spacetime isn't a continuum but a vast collection of discrete, interconnected events, each one a single tick in the universe's quantum clock. Picture reality as an ever-growing web, where every point represents a moment of cause and effect, and every connection between them is a fundamental building block of existence. In this view, the universe's first quantum superposition wasn't a blur of probabilities in smooth spacetime, it was a flickering network of potential causes, each waiting to crystallize into the timeline we know. At its heart, causal set theory tackles one of physics' biggest headaches, the continuum problem. Classical physics treats spacetime as infinitely divisible, like a loaf of bread you can slice thinner and thinner forever. But when quantum mechanics enters the picture, this smoothness breaks down, energy comes in chunks, so why shouldn't spacetime, the theory's answer is elegant: spacetime is born from causality itself. Imagine throwing a handful of sand onto a table. Each grain represents an event, and the way they pile up creates a structure not smooth, not random, but a precise order where some grains support others. In the cosmic version, every grain is a fundamental unit of spacetime, and the relationships between them, which events cause others, define the geometry of reality. Here's where superposition gets wild. In the early universe, before causality solidified, these events wouldn't have had fixed relationships. Instead, they'd exist in a quantum haze, with every possible causal connection playing out at once. It's like a game of dominoes where each tile hasn't just fallen or stayed upright, it's done both, in parallel, until some critical threshold collapses the possibilities into a single, coherent sequence. This quantum causal jitter could explain why the universe initially existed in superposition. Time itself hadn't yet picked a direction. What makes this radical is how it sidesteps the infinities that plague other theories. In general relativity, singularities like the Big Bang break the math, density, and curvature spiral to infinity, but in causal set theory, there's no infinity, because there's no continuum to divide endlessly. The Big Bang becomes the first causal event in a chain, not a mathematical paradox. Some versions even suggest that quantum gravity, the holy grail of physics, emerges naturally from this granularity, with spacetime's smooth appearance being an illusion, like the blur of a spinning wheel's spokes. Critics ask, if spacetime is discrete, why don't we notice the graininess? Proponents point to the Planck scale, where distances are so tiny that any roughness would be invisible to our instruments, like a pixelated image smoothed by distance. Others speculate that quantum fluctuations in the cosmic microwave background might hide fingerprints of this causal structure, waiting to be decoded. The most profound implication: if causal set theory is right, then the universe's first moments weren't governed by equations of motion, but by pure probability, a cosmic dice roll where every possible cause and effect chain flickered briefly before one history won out. And somewhere in the depths of spacetime, those other possibilities might still linger, like shadows of roads not taken, whispering from the edges of reality. What if the universe didn't begin with a bang, but with a scream, a black hole's death cry in another reality, echoing into existence as our own? This is the spine-tingling premise of the black hole genesis theory, a hypothesis suggesting our entire cosmos might be the quantum offspring of a collapsing star in a forgotten universe. Picture this: a supermassive black hole in some distant dimension reaches the end of its life, its singularity stretching and churning under unimaginable forces. According to quantum gravity, what happens next isn't a collapse into nothingness but a rebound, a cosmic phoenix bursting forth as a white hole, spewing out matter and energy in a fiery rebirth. And that eruption that could have been our Big Bang, the math behind this idea is as elegant as it is unsettling. Black holes warp spacetime so severely that time near the event horizon slows to a crawl. From an outside observer's perspective, a dying black hole's final moments could appear frozen, yet inside, quantum mechanics suggests something stranger. The singularity might not be a point of infinite density, but a quantum bridge, a tunnel where matter and energy get scrambled into a primordial soup before re-emerging as a new universe. It's like squeezing a sponge so hard it bursts, not with water, but with an entire spacetime continuum. Now tie this to the holographic principle. If black holes encode all their information on their event horizons, as the holographic theory suggests, then the interior singularity isn't just a grave for matter, but a cosmic womb. The quantum superposition of particles inside wouldn't just vanish, they'd get imprinted onto the fabric of the new universe like a stencil, dictating its initial conditions. This could explain why our universe's fundamental constants seem so finely tuned. They weren't random, but inherited from the black hole's quantum data. White holes play a starring role here, Long dismissed as mathematical oddities, these time-reversed black holes, regions where matter can only escape, never enter, could be the other end of the birthing tunnel. Some models suggest the Big Bang's explosive energy matches what you'd expect from a white hole's sudden eruption. Even more tantalizing is the cosmic microwave background, which some physicists argue shows faint, circular patterns, potential echoes of the parent black hole's event horizon, stretched and faded across 14 billion years. The implications rewrite cosmic history. If true, every black hole in our universe might contain a budding cosmos inside it, each with its own physics, each birthed from quantum chaos. Our universe could be one layer in an infinite Matryoshka doll of realities, stacked within black holes, and somewhere out there, the remnants of our parent universe might still linger, its laws subtly imprinted onto ours like a shadow in the quantum code. Skeptics, of course, raise valid questions. How could a universe's worth of energy fit inside a black hole singularity? Supporters counter that quantum gravity allows for extreme compression. Think of spacetime as a folded sheet, where what seems infinite in one dimension is compact in another. Others ask, where's the proof? The answer might lie in gravitational waves. If our universe emerged from a black hole, its earliest moments could have left ripples in spacetime with a distinct signature, a pattern we might one day decode in detectors like LIGO. The most haunting possibility: if black holes birth universes, then our own cosmic fate, heat, death, collapse, or another rebound, might already be written in the quantum echoes of our origin. We could be living inside a cycle older than time itself, a single note in an endless symphony of creation and destruction, where every ending is just a beginning in disguise. What if the universe's first quantum superposition didn't just collapse forward in time but reached backward, too? That's the mind-bending proposition of the transactional interpretation, a radical quantum theory where the past and future shake hands to create reality. Imagine the early universe as a cosmic auction house, where particles don't just exist in the present, they send out offers into the future and receive confirmations from the past, locking their quantum states into place through a mysterious dance across time. At the heart of this idea is retrocausality, the notion that future events can influence the past just as much as the past shapes the future. Developed by physicist John Cramer in the 1980s, the transactional interpretation flips the script on traditional quantum mechanics. Instead of a wave function collapsing randomly when observed, particles emit, offer waves forward in time and confirmation waves backward, creating a closed loop that solidifies their behavior. Picture throwing a pebble into a pond, but the ripples travel both forward and backward in time, meeting somewhere in the middle to create the splash you actually see. Now apply this to the universe's birth. In those first seething moments, quantum fluctuations wouldn't just flicker randomly, they'd send offers of every possible configuration into the future, waiting for confirmations to echo back. The superposition we think of as uncertainty, that was just the negotiation phase. The cosmic handshake happened when the first confirmations returned, weaving spacetime into a stable fabric. This could explain why quantum mechanics feels so non-local, why entangled particles sink instantly across distances. They're not communicating faster than light, they're linked by transactions that transcend time altogether. Critics pounce on the paradoxes. If the future influences the past, why can't we remember tomorrow? Supporters argue that transactional loops are self-consistent, only confirmations that don't create paradoxes are allowed, like a cosmic editor trimming contradictory plot lines. Others point to quantum experiments with delayed choice, where measuring a particle now seems to alter its behavior in the past. These eerie results align neatly with a universe built on two-way causality. The most staggering implication: if the transactional interpretation is right, the Big Bang wasn't an isolated event, it was the first successful negotiation between time's two arrows, a deal struck across eternity that made our reality possible. And somewhere in the quantum static, those handshakes might still be happening, stitching the present together one transaction at a time. Have you ever played a video game so immersive, so hyper-realistic, that for a split second, you forgot it wasn't real? Now take that feeling and crank it up to cosmic scales, because some of the world's sharpest minds are seriously considering whether our universe might be someone else's simulation. This is the simulated universe argument, a theory that flips the quantum superposition mystery on its head. What if the universe's first quantum haze wasn't a natural phenomenon, but a glitch in the code of an unfathomably advanced computer? At its core, the idea is shockingly simple. If consciousness can one day create simulations indistinguishable from reality, think ultra-advanced VR, then statistically, the odds tilt heavily toward us already living inside one. Picture a future civilization with quantum processors so powerful they can simulate entire universes, complete with self-aware beings. Now ask, if they run 1 trillion simulations, how do you prove you're not in one? The superposition we observe at quantum scales, particles existing in multiple states until measured, might just be the simulation's optimization trick, rendering only what's observed to save computational power. It's like a video game that only loads the graphics when you look at them. The argument gains teeth when you examine quantum mechanics quirks. Why does observation collapse the wave function? In a simulation, that's just lazy programming. Why calculate all possible states when you only need one? The infamous double-slit experiment, where particles behave as waves until measured, could be the universe's equivalent of a mouse cursor hovering over a file icon. The system doesn't bother rendering the full details until you click. Even the speed of light, the universe's ultimate speed limit, might just be the processor's clock rate, ensuring the simulation doesn't overload. But here's where philosophers and physicists clash. Can we ever prove or disprove this? Some, like Neil deGrasse Tyson, argue it's unfalsifiable, a cosmic what if with no testable predictions. Others point to potential glitches. If the universe is coded, there might be rounding errors in fundamental constants, like finding pi equals 3.14 in a chalkboard calculation. Some theorists search for pixelation in spacetime at the Planck scale, or anomalies in high-energy particle collisions where the simulation might cut corners. The ethical implications are dizzying. If we're simulations, are our creators gods or just bored grad students? Do we have free will, or are we NPCs in a cosmic sandbox? And if we one day build our own simulations, does that make us players and pawns in an infinite recursion of realities? The simulation argument doesn't just challenge physics, it rewrites the meaning of existence itself. Yet for all its Hollywood appeal, the theory has heavyweight backing. Elon Musk famously claimed the odds we're in base reality are 1 in billions. Even Nobel laureates like Frank Wilczek entertain it as a serious thought experiment. Whether cosmic truth or existential prank, the simulated universe hypothesis forces us to confront a humbling possibility that the quantum weirdness we've been puzzling over isn't a feature of reality, but a bug in the system, an artifact of something far stranger running in the background. What if the universe's first quantum superposition wasn't a fact of nature, but a reflection of our own uncertainty? That's the provocative twist offered by quantum Bayesianism, or QBism, a theory that treats quantum mechanics not as a description of objective reality, but as a tool for navigating the messy, uncertain edges of what we can know. Imagine standing in a pitch-black room holding a flashlight with a dying battery. Every flicker reveals fragments of the space around you, a chair here, a table there, but never the whole picture. QBism argues that quantum superposition works the same way. It's not that particles are truly in multiple states at once, but that our knowledge of them is inherently incomplete. The universe's first quantum haze, then, wasn't a physical condition, it was a cosmic shrug, a moment before any observer could place their bet on what came next. At its core, QBism graphs the mathematics of quantum theory onto the framework of Bayesian probability. the science of updating beliefs in the face of new evidence. In this view, the wave function, the mathematical entity that describes quantum states, isn't a real, physical thing. It's a personal guidebook, a way for an observer to quantify their uncertainty and adjust their expectations as they gather data. When early cosmologists describe the universe's superposition, QBism would say they're not describing the universe itself, but their own limited perspective on it. The moment the wave function collapsed wasn't a physical event, it was a Bayesian update, a mental shift as new information narrowed the possibilities. This stands in stark contrast to realist interpretations like the Copenhagen interpretation or many worlds theory, which treat superposition as an objective feature of reality. For realists, the universe's quantum fog was a tangible state, a churning sea of possibilities that existed independently of any observer. QBism flips this on its head. There was no fog, only the fog of human ignorance. The universe didn't choose a state at the Big Bang, we did, by asking questions of it. Critics argue this veers dangerously close to solipsism, making reality dependent on individual minds. But QBists counter with a pragmatic defense. Science has always been about models, not absolute truths. Newton's laws don't describe gravity's ultimate nature, they predict how objects fall. Similarly, quantum mechanics might just be humanity's best user manual for a universe that forever hides its inner workings, the theory's most radical implication. If QBism is right, then the universe's first moments weren't governed by quantum laws, they were defined by the absence of anyone to enforce them. Reality didn't coalesce until the first observer, whether a cosmic force, a fledgling life form, or some yet unknown entity, began taking notes. And in that case, the quantum superposition we debate today might just be the echo of a much deeper mystery, the line where knowledge ends and the unknown begins. Imagine a cup of hot coffee left on a counter, steam rising, heat slowly leaching into the air until it matches the room's temperature. This everyday process holds the key to one of physics' deepest mysteries, how time itself might have emerged from the universe's first quantum fog. The thermal time hypothesis flips our understanding of time on its head, proposing that what we perceive as the relentless forward march of causality isn't fundamental at all. Instead, time could be an illusion, a byproduct of thermodynamics, the universe's stubborn tendency toward disorder, prying apart the quantum superposition of its infancy and carving a direction into the void. At its core, the hypothesis suggests that time's arrow isn't woven into the fabric of spacetime, but emerges from the statistical behavior of quantum systems. Think of a deck of cards fresh from the box, perfectly ordered, every suit in sequence. Shuffle it once, twice, and the order frays into chaos. The early universe, in its primordial superposition, was like that pristine deck, every possible configuration equally probable. But as quantum interactions multiplied, the cosmic shuffling began, and a gradient of entropy emerged. That gradient, the thermal time hypothesis argues, is what we now call time. It's not that the universe chose a direction, it's that probabilities stacked up like dominoes, making one outcome overwhelmingly likely. This idea bridges quantum mechanics and thermodynamics in a startling way. In quantum statistical mechanics, systems don't collapse from superposition because of some mystical observer effect. They do so because higher entropy states are statistically inevitable. Picture a million coins flipped at once. They could land in any configuration, but the odds of half heads and half tails dwarf the chance of all heads. Similarly, the universe's initial quantum haze wasn't collapsed by observation, but by the sheer weight of probability favoring certain arrangements over others. The result, an emergent arrow of time, pointing inexorably toward increasing disorder. Critics often ask, if time is thermal, why does it feel so uniform? Why don't we experience time slowing down in low entropy environments, like near absolute zero, proponents counter that entropy isn't just a local phenomenon, it's a global feature baked into the universe's expansion. As space stretches, it creates new slots for disorder to grow, ensuring time's arrow never wavers. Others point to black holes, where entropy reaches mind-bending extremes, as natural laboratories for testing the hypothesis. Near a singularity, where spacetime warps beyond recognition, does time still flow, or does it dissolve back into quantum static, the most haunting implication? If the thermal time hypothesis is correct, then the universe's first moments weren't governed by clocks or causality, but by statistics, a quantum casino where entropy was the house, and time the ultimate payout. And every second that passes might just be the echo of that primordial die roll, reverberating through the ages. What if the universe never actually collapsed from its primordial quantum haze, but instead, every possible version of events played out simultaneously, weaving a tapestry of realities so flawless that we only perceive one coherent thread? This is the mesmerizing promise of the decoherent histories approach, a framework where the universe's first superposition doesn't vanish but branches into parallel timelines so perfectly decohered they never interfere with one another. Imagine a hall of mirrors where every reflection is real, but the glass is so finely etched that no two images ever overlap. In this view, quantum mechanics isn't about things collapsing into reality, it's about us only noticing one slice of a vast, silent symphony of possibilities. At its core, this approach sidesteps the infamous measurement problem, the nagging question of why observation forces quantum systems to pick a state. Instead, it argues that every possible history of the universe unfolds, but most cancel each other out through destructive interference, leaving only the consistent, decoherent paths visible. Think of it like noise-canceling headphones for reality. Countless quantum histories hum in the background, but the ones we experience are the melodies where the static drops away. Applied to cosmology, this means the Big Bang wasn't a single explosion but a near-infinite fan of beginnings, each with subtly different initial conditions. The universe we see isn't the true one, just the one where all the quantum phases align to leave a footprint we can trace. What makes this radical is how it handles time. In standard quantum mechanics, the present moment feels absolute, a wave function collapses now, and reality solidifies, but the decoherent histories framework treats time as a landscape, where past, present, and future are equally real, just filtered through the lens of consistency. The cosmic microwave background, often called the universe's baby picture, wouldn't be a snapshot of one history but a palimpsest of all possible early universes, their contradictions erased by decoherence. It's as if spacetime is a meticulously edited film, where every frame had countless alternate takes, but only the seamless cut made the final reel. Critics argue that without a clear mechanism for why some histories decohere and others don't, the approach feels like sleight of hand. But proponents point to Quantum Darwinism, the idea that certain states proliferate by leaving imprints on their environment as nature's editor, selecting which histories become real for observers like us. Others note that black holes, with their voracious appetites for information, might be natural decoherence machines, shredding inconsistent histories into quantum noise. The most profound implication: if the decoherent histories approach is correct, then the universe's first superposition never truly ended. We're not living in the aftermath of a quantum choice, we're riding one thread of a boundless tapestry, unaware of the other patterns shimmering just out of view. And somewhere in the math, those ghostly histories might still linger, whispering to ours through the static of spacetime. Imagine a river flowing through a dense forest, its current invisible beneath the surface, yet guiding every leaf and twig along an unseen path. This is the essence of the pilot wave theory, a radical alternative to mainstream quantum mechanics that dares to ask you, what if the universe's first quantum superposition wasn't random at all, but steered by a hidden hand? At the heart of this idea lies Bohmian mechanics, a framework where particles aren't ghostly probabilities but real, tangible objects riding atop a secret cosmic tide, a pilot wave that whispers to them where to go. While most quantum theories treat particles as waves of possibility until observed, Bohm's vision restores determinism. Every electron, every photon, even the universe itself in its infancy, had a definite position. It's just that we couldn't see the map guiding them. The theory's origins trace back to the 1950s, when physicist David Bohm grew frustrated with quantum mechanics' reliance on randomness. If particles could truly be in multiple places at once, he reasoned, why do experiments always find them in one spot? His answer was elegant and unsettling. Particles only appear probabilistic because we're blind to the deeper layer of reality, the pilot wave. Think of it like a surfer riding a wave. From a distance, the surfer's path seems unpredictable, bobbing with the ocean's whims, but up close, you'd see the wave's hidden structure dictating every move. In Bohm's universe, the Big Bang's quantum fog wasn't a formless haze, it was a churning sea of these waves, each ripple nudging particles into place like cosmic traffic control. But there's a catch, one so strange it made Einstein himself uneasy. The pilot wave isn't local, it doesn't obey the speed of light or respect distances. A change to one particle's wave instantly affects another across the universe, as if space were just a suggestion. This spooky action at a distance, as Einstein called it, isn't just a quirky, it's the engine driving Bohmian mechanics. When two particles entangle, their pilot waves interlock, creating a shared rhythm that keeps them in sync no matter how far apart they drift. It's as if the universe's first quantum state wasn't a chaotic dice roll, but a meticulously orchestrated dance, with every step planned by waves we'll never see. For decades, mainstream physics dismissed Bohm's ideas as a fringe curiosity until droplets began dancing in oil tanks. In 2005, a team in Paris demonstrated that tiny droplets bouncing on a vibrating fluid could eerily replicate quantum behaviors, from interference patterns to tunneling. These Walker experiments suggested that pilot waves might not just be mathematical fiction, they could have real, observable counterparts. Suddenly, Bohmian mechanics wasn't just philosophy, it was a doorway to testing whether the universe's quantum rules might emerge from deeper, deterministic laws. Yet challenges remain. If pilot waves exist, why haven't we detected them? Critics argue the theory's non-locality clashes with relativity, violating causality's sacred speed limit. Supporters counter that non-locality might not transmit information, skirting paradoxes. Others point to quantum foundations experiments like the Leggett-Garg inequality, which probe whether reality exists independent of observation, a key Bohmian claim. While no smoking gun has emerged, the debate rages on, proving that even after 70 years, Bohm's hidden waves still ripple through physics, the most tantalizing implication. If the pilot wave theory holds, the universe's first moments weren't governed by chance, but by a cosmic choreography we're only beginning to glimpse. Every atom, every star, every flicker of consciousness might trace back to those primordial ripples, a hidden symphony playing beneath the surface of reality, guiding us all along an unseen current. Picture an ocean frozen solid, not just the water, but the very waves themselves, trapped in a perfect crystalline stillness. That's the eerie beauty of a Bose-Einstein condensate, a state of matter where quantum particles lose their individuality and merge into a single, unified quantum wave. Now imagine that happening not to atoms in a lab, but to the fabric of spacetime itself. This is the radical vision of the quantum gravity condensate theory, which proposes that the universe's first quantum superposition wasn't a chaotic frenzy, it was a cosmic deep freeze, where the building blocks of reality locked into a shared, ultra-coherent state. At temperatures colder than deep space, certain particles like rubidium or sodium atoms can be coaxed into this bizarre condition. They stop behaving like discrete objects and begin acting as one gigantic quantum entity. a superatom humming in perfect harmony. Apply this to the birth of the cosmos, and something astonishing emerges. If spacetime itself is quantized, made of tiny, indivisible grains, then the unimaginable heat and density of the Big Bang's earliest moments might have forced those grains into a universal condensate. In this state, distances and directions wouldn't just be fuzzy, they'd cease to have meaning entirely. The universe wouldn't be in multiple places at once, it was all places at once, a singular quantum ripple stretched across existence. Here's where analog gravity experiments come in. Scientists can't recreate the Big Bang, but they can simulate its physics using these condensates in labs. By tweaking magnetic fields or laser beams, they've created sonic black holes, regions where sound waves can't escape, mimicking spacetime's warping near a singularity. More chillingly, they've observed spontaneous quantum fluctuations in these systems, tiny ripples that resemble primordial spacetime foam. It's as if the universe's first moments are hiding in plain sight, encoded in the quantum dances of ultra-cold atoms. But the most electrifying idea, if spacetime was once a condensate, its melting might explain cosmic inflation, the universe's explosive early growth. Like ice transitioning to water, the condensate's breakdown could have released latent energy, turbocharging expansion. This would solve a persistent puzzle: why does the universe look so uniform? A condensate's coherence ensures every part behaves identically, leaving no room for irregularities. Even now, traces of that quantum solidarity might linger in the cosmic microwave background's eerie smoothness. Critics argue that scaling quantum effects to cosmic proportions is a leap. Can spacetime really behave like rubidium in a magnet trap? Supporters point to emergent gravity theories, where spacetime's properties arise from collective quantum behavior, like traffic patterns emerging from individual cars. Others note that condensates naturally exhibit entanglement, offering a bridge to quantum gravity's deepest mysteries. The takeaway is staggering. If the quantum gravity condensate theory holds, the universe didn't just begin with a bang, it awoke from a quantum slumber, shaking off the stillness of perfect unity to embrace the vibrant, chaotic diversity we call home. And in some lab right now, a cloud of atoms a billion times colder than space might hold the key to reliving that first cosmic shiver. Consider a snowflake not for its delicate beauty, but for its stubborn structure. No matter how you twist or turn it, certain properties remain locked in place, immune to the chaos around them. Now imagine that unshakable order baked into the very fabric of spacetime itself. This is the wild promise of topological quantum field theory, a framework where the universe's first quantum superposition wasn't just a fleeting state, but a cosmic fingerprint etched into reality by the unbreakable rules of topology, the mathematics of shapes that stay the same even when stretched or bent. At its core, this theory suggests that the early universe wasn't a formless soup of particles, but a mosaic of topological phases, exotic states of matter where quantum information gets braided into the geometry of spacetime like knots in an infinite-dimensional necklace. The key players here are enyons, bizarre quantum entities that exist only in two dimensions, dancing around each other in ways that defy classical logic. Unlike electrons or photons, enyons remember their interactions not through force or charge, but through the abstract threads they weave in spacetime. Swap two enyons, and their quantum state doesn't just change, it evolves in a way that depends on the precise path they took, as if the universe itself keeps a secret ledger of every twist and turn. This isn't just mathematical poetry. In labs today, enyons are the darlings of quantum computing, where their fault-resistant braiding could revolutionize how we store and process information. But scale this up to cosmic proportions, and the implications are staggering. If the infant universe hosted topological phases, then the quantum superposition we observe today might be a fossil imprint of those primordial braids, a relic of a time when reality's code wasn't written in particles or waves, but in the immutable knots of spacetime itself. Critics argue that our universe has three spatial dimensions, not two, so how could onion-like behavior shape it? Proponents point to higher dimensional analogs, where topological order might manifest as intricate, knotted field lines threading through the cosmos. Others speculate that the cosmic microwave background's faint anomalies could be signatures of these structures, like shadows of a quantum tapestry woven at creation. The most tantalizing idea, if topological quantum field theory holds, then the universe didn't just emerge from quantum chaos, it unfolded like a cosmic origami, its deepest laws creased into existence by geometry so profound, not even time could fray its edges. And somewhere in the quantum static, those folds might still whisper, holding reality together stitch by immutable stitch. What if the universe never needed an observer to snap into focus? What if reality itself had a built-in kill switch for quantum weirdness? That's the spine-tingling premise of objective collapse models, a family of theories where the universe's first quantum haze didn't require a cosmic measuring device or a conscious mind to collapse, it just did. Spontaneously, like a sheet of ice shattering under its own weight, these models propose that superposition isn't a fragile state sustained by isolation, but a ticking time bomb, doomed to implode under the quiet pressure of its own mathematics. The most famous of these, the Gerardi-Rimini-Weber or GRW model, dares to rewrite quantum mechanics with a single brutal rule: particles can't stay in superposition forever. Every now and then, randomly, unpredictably, their wave functions collapse on their own, snapping from fuzzy probabilities into concrete reality. The numbers here are staggering. For a single electron, this might happen once every 100 million years. But scale that up to the trillions of particles in a dust speck, and collapses happen constantly, creating the illusion of classical solidity. Apply this to the early universe, and the implications are profound. That primordial quantum fog, it wasn't waiting for an observer, it was a countdown clock, each spontaneous collapse chipping away at the superposition, until only our familiar, classical cosmos remain. Here's where it gets even wilder. These collapses aren't gentle. GRW suggests each event slightly heats the particles involved, an effect so minuscule it's nearly impossible to detect, yet over cosmic scales, it could add up. Some theorists speculate this might explain dark energy's mysterious push on the universe's expansion. Others argue that if collapses are tied to mass, they could warp spacetime itself, leaving faint gravitational ripples we might one day trace in detectors like LIGO. But the real controversy lies in the math. Traditional quantum mechanics treats wave function collapse as a ghost in the machine, necessary but unexplained. Objective collapse models banish the ghost by baking collapse into the equations. The trade-off, they're nonlinear, breaking quantum theory's elegant symmetry. Critics argue this is like using a sledgehammer to crack a walnut, solving the measurement problem by brute force. Supporters counter that nature isn't obligated to conform to human aesthetics, pointing to experimental efforts like the underground GRW hunt in Gran Sasso, where scientists monitor nanoscale crystals for the telltale heat spikes of spontaneous collapses. The most haunting implication: if objective collapse is real, then the universe's first moments weren't a quantum democracy, where all possibilities held equal weight. They were a slow-motion avalanche, tumbling toward classical reality, one random collapse at a time. And somewhere in the vacuum of space, those collapses might still be happening, silent and invisible, like the universe quietly reminding itself what's real. Imagine the universe not as a collection of particles or waves, but as a cosmic processor humming with trillions of quantum bits, a vast, self-programming computer where every event, from the birth of stars to the firing of neurons, is just information being rewritten. This is the quantum information paradigm, a vision so radical, it suggests the universe's first superposition wasn't some exotic physical state, but the initialization of history's most ambitious computation. At the Big Bang, the cosmos didn't just ignite, it booted up, setting qubits of spacetime flickering in a primordial algorithm we're only beginning to decode. The roots of this idea stretch back to John Wheeler's famous slogan, "It from bit," the notion that every particle, every force, might ultimately be a manifestation of information. Today, qubit cosmology takes this further, modeling the early universe as a quantum circuit, a network of entangled bits performing operations that literally constructed reality. Picture the cosmic microwave background not as an afterglow of heat, but as readout data from the universe's first processing cycle, its fluctuations akin to computational noise frozen in time. In this view, superposition wasn't a bug, it was the system's way of exploring multiple solutions simultaneously before committing to an output. Here's where it gets bizarrely practical. Quantum computers in labs already mimic this cosmic behavior. When a quantum processor tackles a problem, it leverages superposition to test countless possibilities at once. Scale that up to the universe's birth, and you get a chilling possibility. The Big Bang might have been nature's version of a quantum algorithm executing, with inflation acting like an optimization subroutine, pruning unfavorable outcomes until only a stable, classical universe remained. Some theorists like Seth Lloyd argue the cosmos could still be computing, its laws of physics nothing more than the consistent rules of a grand information processing protocol. But what does it mean for reality to compute itself? Think of a chess game where the board, pieces, and rules emerge from the gameplay itself. In qubit cosmology, spacetime isn't the stage for computation, it's the result. Entanglement between quantum bits could have woven the fabric of space, while quantum gates, the operations that transform qubits, might correspond to fundamental forces. Even time's arrow might be an illusion, a side effect of increasing complexity as the universe processor churns through states. Critics push back, if the universe is a quantum circuit, where's the hardware? Supporters counter that this misses the point. Reality might not need hardware in the conventional sense. Just as a video game world doesn't rely on physical pixels but logical relationships, the universe could be made of the information itself, with qubits as the ultimate substance of existence. Others note eerie parallels with holographic theories, where the universe's 3D richness is projected from a 2D boundary, perhaps the cosmic hard drive where information is fundamentally stored. The most electrifying implication, if the quantum information paradigm holds, the mysteries of dark matter or dark energy might not be missing physics, but undocumented code, glitches in the cosmic program we've yet to reverse engineer. And if we ever crack nature's source code, we might not just understand the universe, we could learn to rewrite it. Picture the branching veins of a leaf, the jagged edge of a coastline, or the spiraling arms of a galaxy, patterns that repeat themselves at every scale, from the microscopic to the cosmic. This self-similar symmetry, known as fractal geometry, isn't just a quirk of nature, it might be the universe's deepest operating system, written into the quantum code of reality itself. The fractal quantum universe theory proposes something staggering. The superposition we observe at the smallest scales isn't confined to particles, it echoes upward, threading through atoms, stars, and galaxies in an unbroken cascade of quantum ambiguity. At its heart, this idea ties into one of physics' most powerful tools, the renormalization group. Think of it as a cosmic zoom lens. When physicists study quantum fields, infinities often crop up in the math, an annoying side effect of probing infinitely small scales. Renormalization smooths these rough edges by zooming out, revealing how phenomena change at different levels of magnification. What's shocking is that certain quantum systems, like those near phase transitions, exhibit fractal behavior. Their patterns look identical whether you're examining a lab sample or the universe at large. Apply this to cosmology, and the implications are profound. If the universe's quantum properties scale fractally, then superposition isn't just a tiny anomaly, it's a universal blueprint. Consider the double-slit experiment. where particles act as both waves and particles until measured. Now imagine scaling this up. Could entire galaxies exist in superposition, their positions undecided until some cosmic measurement occurs? Wild as it sounds, the math doesn't forbid it. Fractal scaling suggests that the quantum weirdness governing electrons might also shape galactic clusters, with each level of complexity inheriting the probabilistic nature of the level below. It's as if the universe is a hall of mirrors, where every reflection, no matter how vast, retains the quantum flicker of the original. Critics argue that decoherence, the process by which quantum systems lose coherence through interaction, should erase such effects at macroscopic scales. But fractal enthusiasts counter with strange cosmic coincidences. The distribution of galaxies, for instance, isn't random. It follows a hierarchical clustering that mirrors fractal mathematics. Even the cosmic microwave background's fluctuations show hints of self-similar patterns, as if the universe's earliest quantum jitters imprinted their structure on everything that followed. The most mind-bending twist: if the universe is fractal at its quantum core, then the distinction between small and large might be an illusion. A single entangled particle pair and two synced black holes could be playing by the same rules, just at different volumes. And somewhere in that infinite recursion, the universe's first superposition might still be echoing, scale after scale, a whisper never quite fading away. Among the universe's most elusive particles, neutrinos, those ghostly, nearly massless travelers, might hold a clandestine key to how reality snapped out of its primordial quantum haze. These cosmic phantoms, capable of slipping through light years of lead without a trace, have a bizarre quirk: they shapeshift as they fly. One moment an electron neutrino, the next a muon or tau neutrino, oscillating between flavors like a chameleon cycling through colors. This phenomenon, neutrino oscillation, isn't just a subatomic curiosity. It could be a relic of the universe's first quantum superposition, a process so pivotal it may have tipped the scales between matter and antimatter, sculpting the cosmos into what we see today. At the Big Bang's searing temperatures, neutrinos weren't just abundant, they were likely the first particles to decouple from the quantum soup, free to roam while other particles remained tangled in the fray. Here's where leptogenesis enters the story. Current theories suggest that in the universe's first moments, heavy, hypothetical particles, like the yet undetected right-handed neutrinos, decayed unevenly, producing slightly more matter than antimatter. But here's the twist: neutrino oscillations could have amplified this asymmetry. Imagine a pendulum swinging left and right, but every time it swings left, it gains a tiny extra push. Over eons, those minuscule biases add up. Neutrino oscillations, with their flavor-switching dance, might have acted as that pendulum, nudging the universe toward a matter-dominated fate. The mechanics are mind-bending. In quantum field theory, particles and antiparticles are like reflections in a mirror, nearly identical, but with opposite charges. Yet neutrinos blur this line. They're the only particles that might be their own antiparticles, a property called Majorana mass. If true, their oscillations wouldn't just change flavors, they'd flicker between particle and antiparticle states, weaving a quantum tapestry where matter and antimatter weren't perfectly symmetrical. This slight imbalance, frozen into the universe as it cooled, could explain why everything around us, stars, planets, even our own bodies, is made of matter, with antimatter vanishingly rare. Critics argue that neutrino masses are too small to drive such cosmic consequences, but supporters counter with the seesaw mechanism, a theoretical framework where the lightness of ordinary neutrinos implies the existence of ultra-heavy counterparts, particles so massive they'd have dominated the early universe's energy budget. These heavy neutrinos, decaying asymmetrically, could have flooded the cosmos with matter, while their oscillations imprinted a quantum memory into spacetime itself. The echoes of this process might still be detectable. If neutrinos help break the universe's symmetry, their oscillations should have left faint fingerprints in the cosmic neutrino background, a relic sea of these particles, similar to the cosmic microwave background but far colder and nearly impossible to observe. Future experiments like Ptolemy or Dune aim to catch whispers of this background, hunting for distortions that could confirm leptogenesis, the most poetic possibility. Neutrino oscillations might not just be a footnote in cosmic history, they could be the universe's oldest clock. Every time a neutrino oscillates, it's replaying a rhythm set in motion when reality was still a quantum fog, a rhythm that quietly ensured there was something rather than nothing. And in every flicker of these ghostly particles, we might be witnessing the faintest echo of the universe choosing its own existence. Think of the cosmic microwave background as the universe's oldest photograph, a faded snapshot from when reality was just 380,000 years old. But what if those faint microwaves aren't just a relic of heat? What if they're quantum echoes, a sprawling environmental ledger that helped decide which version of the universe would survive? Quantum Darwinism suggests that the universe's first superposition didn't collapse randomly, it was sculpted by countless interactions with particles like these photons, each one acting as a silent scribe recording the quantum state of the early cosmos. Here's how it works. In the primordial plasma before the cosmic microwave background formed, every particle was entangled in a roiling quantum soup. Electrons and protons danced in superposition, their positions and energies undecided. But as the universe cooled, photons finally broke free, streaming outward in all directions, and crucially, they carried with them imprints of the matter they'd last touched. Each photon became a tiny, involuntary witness, its properties shaped by the quantum states it encountered. Over billions of years, these photons would crisscross the cosmos, their paths weaving through galaxies and gas clouds, their interactions with matter becoming a vast, distributed record of which quantum configurations were stable enough to leave consistent traces. This is environmental decoherence on a cosmic scale. Just as a single drop of dye in a glass of water eventually colors the entire liquid, the photons of the cosmic microwave background acted as the universe's ultimate environment, measuring quantum states through relentless interaction. The more a particular configuration could imprint itself on these photons and on other particles like neutrinos and dark matter, the more it resisted decoherence. Unstable or inconsistent quantum states, unable to leave clear environmental records, simply faded away like whispers drowned out by a chorus. The result: a universe that appears classical not because consciousness observes it, but because the cosmos itself has been voting on reality through every particle collision and photon emission for billions of years. The eerie beauty of this process lies in its universality. Every time a modern telescope detects a photon from the cosmic microwave background, it's not just seeing ancient light, it's reading a page from quantum history. The slight temperature variations in that light, often mapped as colorful splotches in astronomy visuals, might encode more than density fluctuations. They could be the fossilized remains of the universe's first quantum decisions, a mosaic of choices amplified by environmental consensus. Even now, as new stars form and black holes merge, their quantum states are being tested against the environment, with only the most resilient configurations surviving. Critics often ask, if quantum Darwinism shaped reality, why does the cosmic microwave background look so uniform? Shouldn't there be patches where different quantum outcomes dominated? The answer lies in the universality of the photon bath. Just as Darwinian evolution converges on similar solutions across isolated ecosystems, wings evolving multiple times on Earth, environmental decoherence tends to favor certain stable states universally. The photons didn't just record local quantum events, they homogenized them, spreading consistent imprints across the sky through their infinite scatterings. The most profound implication: if quantum Darwinism holds, the universe didn't just emerge from superposition, It performed a slow motion measurement on itself, with every particle acting as both observer and observed. And those microwaves bathing the cosmos, they're not just the afterglow of creation, they're the universe's oldest democracy, a light-born tally of quantum votes cast when time was young. Imagine a spinning coin balanced perfectly on its edge, motionless, caught between heads and tails in perfect symmetry. Now picture that same coin wobbling slightly, then clattering onto the table, forced to choose a side. That moment of decision, that breaking of symmetry, might be the key to understanding how the universe snapped out of its primordial quantum haze. This is the symmetry-breaking scenario, a theory suggesting that the universe's first superposition didn't collapse randomly, it tipped, like a cosmic coin, nudged by the invisible hand of physics itself. At the heart of this idea lies one of nature's most powerful concepts, spontaneous symmetry breaking. Think of a crowded party where everyone is evenly spaced, chatting in all directions, a perfectly symmetrical scene. Then someone starts a whisper chain and suddenly, all heads turn toward the source. The symmetry hasn't been broken by an external force, it's collapsed from within, driven by the system's own dynamics. In the early universe, this same principle might have transformed a seething, symmetric quantum fog into the lopsided reality we recognize today. The Higgs field is the star player here. Today it's the reason particles have mass, but in the universe's first moments, it was a simmering quantum field, hovering in a state of perfect symmetry, like a pencil balanced on its tip. As the cosmos cooled, the Higgs field underwent a phase transition, tumbling into a lower energy state, a cosmic game of musical chairs where the music stopped, and the field chose a value. That choice didn't just give mass to particles, it might have shattered the universe's superposition, locking in the fundamental forces and particles we know. The Higgs wasn't just a spectator, it was the scalpel that carved classical reality from quantum potential. Phase transitions are everywhere in nature, water freezing into ice, magnets aligning their poles, but the universe's first symmetry breaking was something grander. Picture a supercooled liquid, poised to crystallize at the slightest disturbance. The early cosmos was like that, a metastable quantum soup, humming with unrealized possibilities. Then somewhere, a tiny fluctuation, perhaps a random quantum twitch in the Higgs field, triggered a cascade. Regions of spacetime chose their broken symmetries, forming bubbles of classical reality that expanded and merged, like ice crystals spreading through slush. The boundaries between these bubbles, they'd have been cosmic defects, topological wrinkles in spacetime, faint scars from the universe's quantum adolescence. Critics might ask, if symmetry breaking was so universal, why does the cosmos seem so smooth? Shouldn't there be chaotic patches where different symmetries won out? The answer might lie in inflation, the universe's explosive early growth. Like a cosmic iron smoothing out wrinkles, inflation could have stretched these primordial imperfections so thin they became nearly undetectable, leaving only faint echoes in the cosmic microwave background. The most profound implication, if the symmetry-breaking scenario is correct, the universe didn't just stumble into classical reality, it organized itself, like a flock of birds suddenly wheeling in unison. And somewhere in the quantum static, those unmade choices might still linger, whispering of roads not taken. What if the early universe was trapped in a state of quantum suspense, not by chance, but by its own frenetic energy? This is the eerie promise of the quantum Zeno effect, a phenomenon where constant observation can freeze a system in place, like a flickering light bulb stuck mid-flash if you stare at it too often. Applied to cosmology, it suggests that the universe's first superposition might not have collapsed, it could have been pinned there, suspended by the relentless buzz of primordial particle interactions, acting as a kind of cosmic paparazzi, snapping endless quantum snapshots before reality could move. The effect gets its name from Zeno's ancient paradox, where an arrow in flight is argued to be motionless because at any instant, it occupies a single point in space. Modern quantum mechanics reveals a bizarre parallel. If you measure an unstable particle's state rapidly enough, it literally can't decay. The act of observation resets its quantum clock, like a snooze button for reality. In labs, this has been demonstrated with atoms. Hit them with laser pulses every nanosecond, and they'll stubbornly refuse to transition to lower energy states. Now scale this up to the universe's birth. In those first seething moments, particles weren't just sparse and solitary, they were packed tighter than neutrons in a star, colliding trillions of times per second. Each collision, each exchange of energy, could have acted as a makeshift measurement, freezing the cosmos in a quantum limbo where time itself struggled to flow. Here's where the early universe's chaos becomes its own cage. Normally, quantum superpositions decay as systems interact with their environment, a process called decoherence. But if interactions are too dense, too frequent, they can have the opposite effect, like a juggler adding so many balls to the routine that none ever hit the ground. Cosmological models suggest that in the first fraction of a second after the Big Bang, the density of matter energy was so extreme that particles couldn't move without bumping into something. Every quark, every gluon, every photon was effectively observing its neighbors, creating a feedback loop that might have artificially prolonged the universe's quantum haze. The implications rewrite cosmic history. If the quantum Zeno effect gripped the early cosmos, then the transition to classical reality wasn't a smooth fade, it was a phase transition triggered by the universe's expansion, finally outpacing particle interactions. As spacetime stretched, collisions grew sparse, and the cosmic paparazzi thinned out, allowing quantum states to finally evolve. This could explain why the universe seems so uniform. It wasn't just cooling from a hot birth, it was thawing from a quantum deep freeze, its initial conditions locked in place until the spotlight of observation dimmed. Critics argue that treating particle collisions as measurements stretches the definition of observation, but supporters point to emergent phenomena in condensed matter systems, where collective behavior can mimic measurement-like effects without any conscious observer. Others speculate that this effect might have left fingerprints in the cosmic neutrino background, where relic particles could carry traces of their delayed decoherence. The most poetic idea, if the quantum Zeno effect held sway, then the universe's first moments weren't a blur of change, they were a cosmic still life, a painting frozen until time itself gained the freedom to flow. And in that stillness, the seeds of everything, galaxies, planets, us, might have waited, suspended between possibility and reality, until the cosmos finally looked away. What if the greatest illusion of all isn't some magician's trick or virtual reality but time itself? The final theory takes us to the edge of comprehension, where clocks stop ticking, beginnings and endings blur, and the universe's first superposition never truly collapsed because there was no when for it to collapse into. This is the timeless quantum universe, a vision so radical it dissolves the flow of moments into a single, frozen now, an eternal tapestry where every event that ever was or will be simply is. At the heart of this idea lies Julian Barber's revolutionary work, which strips away time as a fundamental feature of reality. Imagine a cosmic gallery where every possible configuration of the universe, every arrangement of particles, every flicker of energy hangs like a still painting. The Big Bang isn't the first frame in a movie, it's just one image in an infinite exhibit. What we perceive as time's passage, that's merely our consciousness gliding from one frame to another, creating the illusion of motion like a flipbook in the dark. Barber's universe has no before or after, only a vast here, where quantum superpositions aren't transient states but permanent features of a reality too grand for clocks. The Wheeler-DeWitt equation, born from the marriage of quantum mechanics and general relativity, takes this further by erasing time entirely from its mathematics. When physicists John Wheeler and Bryce DeWitt tried to describe a quantum state of the entire cosmos, their equations returned something unsettling. a universe frozen in an eternal present. No ticking and no expansion, no decay, just a static quantum wave function encompassing all possible configurations of reality at once. It's as if the universe is a locked safe, and time is the combination we invented to make sense of the dial's spin. But how could a timeless universe explain the vibrant, changing world we experience? Enter the concept of time capsules, special configurations in Barber's gallery that appear to contain memories, trajectories, and causality. Our brains, cobbled together by evolution, might be hardwired to stitch these isolated frames into a narrative, like a detective reconstructing a crime from snapshots. The sensation of time flowing, just an evolutionary shortcut, a way to navigate the timeless quantum soup without drowning in its infinite stillness. Critics argue that without time, concepts like cause and effect crumble. If the past and future are equally real, why can't we change history? Supporters counter that change itself is the illusion that every moment exists independently, and our perception of influence is just the way certain frames relate within the gallery. Even entropy, time's arrow in thermodynamics, might be a local phenomenon, a feature of our particular time capsule, rather than a universal law, the most haunting implication. If the timeless quantum universe is real, then the superposition we've spent 30 theories unraveling wasn't a phase the universe passed through. It's the eternal condition of existence, a truth we've been blind to because our minds are trapped in the flipbook. The quantum haze never lifted, we just learned to mistake one page for the past and another for the future, and somewhere beyond the illusion, the universe's first question still hangs in the air, unanswered, not because it's unsolvable, but because there was never a when for the answer to arrive. From the cosmic courtroom of Quantum Darwinism to the timeless quantum gallery of Barber's vision, we've journeyed through a kaleidoscope of realities, each theory offering its own breathtaking answer to the universe's first quantum whisper. Some paint the dawn of existence as a hologram rendered on distant spacetime walls, while others imagine it as a fractal echo or a simulation booting up in some higher dimensional server. There are theories where black holes birth universes like cosmic matryoshka dolls, and others where spacetime itself is a crystal forged from quantum threads. The sheer variety isn't just scientific speculation, it's a testament to human creativity, our relentless drive to stare into the void and ask, how? What's astonishing isn't just the diversity of answers, but how each lens reshapes the question. For every physicist who sees superposition as a glitch in reality's code, another finds it the universe's deepest truth. Some frameworks treat time as an illusion, while others weave it from entanglement or entropy, and yet beneath these contradictions lies a unifying thread, the recognition that quantum mechanics isn't just a tool for equations, it's a mirror reflecting our own limitations, showing us how much we still don't understand about the stage we call reality. So which theory sings to you? Does the elegance of the holographic principle pull you in? Or does the brutal simplicity of objective collapse feel more satisfying? Maybe you're drawn to the cosmic poetry of cyclic universes, where every ending births a new beginning, or perhaps the idea of a simulated universe, with all its existential dread and wonder resonates deepest. There are no wrong answers here, only doorways to deeper curiosity. This is where the conversation truly begins. Drop your favorite theory in the comments, or better yet, tell us why it captivates you. Did we miss a mind-bending idea you've encountered? The universe's origins aren't just a puzzle for physicists, they're an invitation for all of us to play with possibilities, to question, and to imagine. Because in the end, the most thrilling part of science isn't having all the answers, it's the collective journey of asking better questions. Who knows? The next revolutionary theory might start as a spark in someone's mind, maybe even